Recordings rolling. It's Wednesday, January 14th. So there's one last key topic I got to cover with you guys, which is rotational kinetic energy. Right? And that's the very last line on this page. Right. So take us a while, but we've knocked out all these. Right. So the top half of this chart refers to rotational kinetic motion. You guys remember we've had this turntable, right? I'm seeing angular displacement, angular velocity, angular acceleration. Right? We got these formulas, so these kinematic formulas. Right? That's the top half. Okay. Then we talked about rotational inertia. You guys remember those rotational inertia sticks that I passed around? They're still over there inside of the room, by the way. You want to shake us back and forth. Something about mr squared. That takes the place of, well, what mass used to represent in linear motion, how much inertia. Okay. We got torque, R cross F. Right? So like opening a door, turning a wrench. Right? And there's also this torque resultant I times alpha kind of takes the place of Newton's second law of motion, F equals ma. Right? But now we're rotating. Right? Yesterday we talked about this angular momentum. Guess remember that's capital L, I times omega. So kind of takes the place of linear momentum, P equals mb. Okay? Angular momentum is conserved. You guys remember a figure skater goes into a spin, pulls their arms in, they speed up spinning. Right? That's explained by this. Right? And here's the one we're getting to today. There's energy involved in rotation. So if I roll this ball across the floor, or like roll the cylinder or the gyroscope to spin the gyroscope, right? It takes some work, that's to say some energy to get it to spin, and now there's mechanical energy stored in this spinning object. Right? How much? Well, if you look at the formula, it's also analogous to the linear formula. So back last semester, I remember energy motion was 1/2 mv squared. Right? Now it's 1/2 I omega squared. See, the I takes the place of the m, omega takes the place of the v. Right? You guys know that? Right. All right, so that's a quick rundown. All right, but here I got to do the rest of the agenda with you guys. So, all right, so gonna do some posters. We'll solve a little bit today, and then maybe get to the textbook puzzles today. I got those out ready to go. Right. My plan tomorrow is to do a bunch of more textbook puzzles with you guys, and also there's a short lab I want to fit in at the other class, center math. So that'll be tomorrow. Okay. Oh, see, Friday I'm doing different things, different classes. So I've got some different ideas with you guys Friday. Might be more puzzles, or might throw you guys a real challenge question. Okay? But your guys' quiz is going to be in class, and it's going to be over 2 days. And so, guys, it's a little different. So you guys know that there's no school Monday for Martin Luther King Day. And then Tuesday and Wednesday, it's going to be a 2-day quiz. So you get 6 questions on one day and 6 questions on the other day. It'll be collectively 100 points altogether. So on Tuesday, look for questions related to kinematic motion. Okay, that's this type of stuff. Right? Kinematic motion, like turntables. Okay? And also torque and rotational inertia. Okay? Wednesday, look for angular momentum and rotational kinetic energy, which of course I'm covering today. Right? And I'm almost finished putting that quiz together. I'm designing to get it home. Right? So I will definitely have that for you guys on Tuesday and Wednesday. Right? Any questions about the agenda, what we're doing? Okay. All right, so let's jump into these. Okay, so what's a good way to think about energy? Well, I do remember that work was a transfer of energy. So if it took some work to, say, get a turntable to spin, maybe that could give some kind of insight as to what kind of energy we're talking about, like making rotational sense. So give this turntable spin. Okay. Next up, one setup I remember that we were doing yesterday is, what if I wind a string around, around, and around, and fill up the string? And start speeding up spinning. If I keep applying a force in the string, therefore a torque. Right? And so let's go down. I have a derivation for you guys here. Okay. So do you guys remember this from last semester? Work as force times distance. You guys remember that? Right. For example, if you lift something some height, right, takes some energy to do that. That's work. Right. Right. Okay. Here's my turntable, and I have a string wrapped around it, and I'm applying a force at this radial distance. Okay. Now let's suppose that I end up turning this whole thing as a result some angle theta. You guys see angle theta there? Right. If you follow a point on the outside, you also say like how far did the string move? Right. That could be this distance d. Right? Is that true also? Okay. So how can I get maybe the work, not in terms of force and distance, but maybe in terms of a torque I applied or this angle theta, right? In terms of angular values. So let's do some substitutions. Now the first substitution is going to be this distance d right here. Well, on this poster I call it x, but it's the same idea. Right? Do you guys remember what is x in terms of theta? And how does it go? Theta times r, right?
Yeah.
Right. In fact, you guys have known a specific version of this for many years. Everybody knows circumference equals 2 pi r, right? Now that's exactly one trip around, but what if I want to go any trip around? Right? So I'm going to substitute for that d right there. I'm going to call it r theta. Is that okay? Okay. And now I have these three variables multiplied, but I can group them together differently. Guys, what is that right there? That force times that radial distance. What does that give me?
Torque.
Torque. Yeah, that's torque. Okay. Also, the fact that these are always at right angles. That's true whenever you wind a string around a turntable. Okay, so I can replace that r cross f with torque. Okay. Now I have torque times angle. Okay, so it's a different perspective on work. Here. Now, guys, the catch is for theta, guys, suppose theta is 30 degrees. Can I plug in 30 in my calculator for that angle? No, 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 no. No, right? Because you can't put in degrees here. You can only put in what unit? Radians. Has to be in radians, right? Not degrees, not revolutions, which are different ways to describe theta. But in the calculator, this has to be in radians, right? You're only allowed to use degrees. Have you guys ever noticed that? Ever since the very first day of school, you can only use degrees if it's inside a trig function like sine, cosine, or tangent, right? Outside of that, it has to be in radians. All right, so we got that. Okay. Now I'm going to walk you guys through some of these puzzles. I'm going to show you guys just like forest for the trees, how to think about these in terms of variables. Okay? And then we'll solve one at the end of the stack of posters, right? But I really want you guys to see the big picture and think like how do you consider energy working in a rotating system, right? And I've got a few classic physics stories. So one classic physics story is, what if I have this disk up here, which does, so this pulley, which does have a significant rotational inertia, which is different from last semester. Last semester we had these massless frictionless pulleys. You guys remember those Atwoods we set up? This looks kind of Atwoody, right? But now this has some heft to it, has some mass, has a radius. Okay? I'm going to tie a string round, and then drop the string down and tie it to this bucket, right, which has its own weight, which is going to pull down. Now, guys, is this bucket going to be accelerating down once I let it go? Accelerating down? Show of hands. How many of you guys think the bucket is accelerating? Yeah, right. You can see it from this diagram anyway. Guys, which force is bigger, the weight down or the tension pulling up? Yeah, the weight down is more than tension up. So it's like a downward accelerating elevator, sort of. Right? What if you were an ant crawling around in that bucket? Would you feel a little bit lighter, a little bit heavier than your usual weight? Right. Yeah, you'd feel a little bit lighter. The scale reads a little bit light. Yeah. Okay. Because what force is actually acting at the edge of this pulley? Is it the full weight or is it the tension? Yeah, only the tension. So maybe the weight's like 10 newtons, maybe the tension's like 7 newtons. There's a 7 Newton force pulling down. Okay, so you guys said. Right. And I'm going to say, oh, well, okay, you guys see my setup here. I'm doing conservation of energy. Now, I remember last semester, one question that was really primed for the setup was, what's the speed of the object as a function of the height that it fell? Do you guys remember that? Right. You guys remember the Galileo question? Galileo goes to the edge of the Leaning Tower of Pisa, right. Holds out this object and he drops it. And the question was, what was the crash speed as a function of the tower height? You guys remember that? Okay. So maybe I want to answer a question like that. Like if the bucket's fallen some height change, what's the speed of the bucket? Maybe that could be the question. Okay. Okay. I want to see if you guys can figure this out. You guys got paper out, right? You guys got paper? Okay. So can you piece together a conservation of energy equation that could maybe eventually be used to answer that question? What's the speed of the bucket after it's fallen like so many meters, right? If you guys can get that, then I'll be pretty happy. Right? So where would the energy come from in the system? Okay, so I hooked up the bucket to the rope. I'm going to drop the bucket. It's going to start falling. Okay. What's supplying the energy? What formula is that going to be? Okay. And then when the bucket is in motion, it's falling, falling, falling. Where does that energy sort of go? Okay. Oh, I should give you guys a hint too. There's one source of energy I'm looking for. Okay. So something equals, okay. And then where it goes is actually going to be in two places, and you're going to add them up. So some source of energy goes into something and something. I'm just looking for variable forms for these. Some of them might be on this page. Do you guys remember last semester there was that conservation of there were forms of energy there. I think I can dig it up real fast. Where'd it go? Notes. Here it is. Right. You guys remember this page right here? Actually, you know what? I think you can construct the equation I want you to create just from that page. Okay. So something to do with these guys right here. Okay. Can I kind of get all these on here at the same time? Here, can. Yeah, that all fits. Okay. All right, so one more trip around the room. See who correctly constructed that equation I'm looking for? Um, close. Okay. So, figure that. Do I figure that? It's the guy that. Ooh, close. Almost. Okay. Some of you guys are close. I don't think anybody's got it 100% exactly. So, you guys know these are all energy terms. Okay. So, what do you guys think is the source of energy as you're about to drop the bucket? What type of energy in the system? Gravitational potential. Okay, so that could be mgh. Okay. Where the sim refers to the mass of the what? What do you think?
Bucket.
Yeah, the bucket. Right. Now this disc also has mass, but it's not really changing its height. So, right. But the bucket is changing height. So that's the source of the energy. Oh, and where does that energy go? Well, guys, as the bucket's falling, is it speeding up? Does the bucket have a linear kinetic energy? That is true. Okay. So there's a 1/2 mv squared of the bucket. Okay. Guys, as this bucket's falling faster, is the disk also rotating faster?
Yeah.
Right. And if you look over here, what's the formula for energy of a rotating disk?
Inertia.
Yeah, 1/2 I omega squared. Yeah, and that looks like that 1/2 I omega squared. Great. And remind you guys too. I think you guys are probably onto this, but this I right here. See, is it? Get these out of. Okay. Hang on. This is what I'm looking for. Here it is. Okay. You guys see this eye of this pulley right here? Okay. Isn't this pulley basically this shape? So like 1/2 mr squared. Okay. So if you were given the mass of the pulley, the radius of the pulley, and also this expression, that's where this I comes from. So you can have a number for it. Okay. So in kilogram meters squared. All right. Are you guys good with that setup? Here's the source of the energy. And then as the bucket falls, it has this and this going on. Okay. Okay. That's really big picture what I want you guys to see. But how does this finish off? I'll show you guys step by step. Okay. How about this? Guys, critical thinking here. As the bucket's falling faster and the wheel's turning faster, is this V and this omega, are they related to each other?
Yeah.
Yeah. Do you guys think that's the connection right there? Right. So I could substitute one in terms of the other. Like they're not independent. Right. And let's say I want to solve for V. Like what's the speed of the bucket? Can I find omega by doing V divided by R? Right. So you do that. I think it's the next step on this page. Yeah, that's right here. Okay, and it's all V squared, so it's V squared there. Right. Now between here and here, I skipped about 2 or 3 algebra steps. But this V shows up here and here. And if you do some algebra, which you've done a bunch of in this class, you can eventually solve for the speed like this. Okay. So, okay. But really what I want you guys to get out is this like big picture. Okay, here's the source of energy, and here's where it goes. And some of the energy, in fact, makes this wheel rotate. Okay. Now, next poster, I have the same picture, maybe it's the same scenario, but there are a lot of other questions you could ask other than what's the speed of the bucket. Okay. And in general, I have this whole system set up. Right? In fact, my AP class here, I'll just show you guys real fast what my AP students are doing. Out of their book, they have a question that looks a lot like that. This weight. Okay? And the textbook threw some numbers at them, and we solved this. It ended up being like a 4 equation system of equations. Okay? We were able to find all these things from it. Okay? So, like, in principle, it could be asked a question like that. Right. All right. Might hold on to this one. Let's do a different scenario that could also involve rotation. Okay. Ooh, this one's fun. I might possibly do this as an activity with you guys one day. I'll see how things pace out. But this could be a fun one. Is what if you have a toilet paper roll, and if you ignore the fact that it has kind of a donut hole in the middle, it's pretty close to a solid cylinder. It's a common approximation. Yeah. What if you grab onto the paper and you just drop it and starts unraveling? Right? Oh, you could ask a question like, hey, how about speed as a function of height change? That could be a question. You could ask a question, how much time does it take to hit the ground? You could say, what is its acceleration compared to, ooh, guys, how does it compare this? What if separate from that, you just have a roll of toilet paper, like same mass and radius, blah, blah, right? And you just drop it, right? And it free falls. Free falls. Okay. Guys, which is going to hit the ground first? Guys, critical thinking here. Which hits ground first? The one you drop and it free falls, or the one that you hold onto the paper and it unrolls? Which? How many of you guys think the one that I drop and it free falls hits ground first? Who says that? Yeah, yeah, right. Which might tell you something about maybe if I want you to know what's the acceleration of this, like the linear acceleration of the center point. With this, so back to the one that's unraveling. Would it have an acceleration overall that's less than Earth gravity? I think it would. Right? This whole process slowing down. Right? There's a few ways to think about this, and also different questions you could deviate to answer. Right? But let's do an energy setup and see. Well, we'll just kind of play around with this and see where it goes. Because let's do another energy setup. Energy setup. So on your paper, and I think it follows. Let's see. Yeah, it's also going to follow the same format. One form of energy turns into something plus something. Okay, so there's like a supply of energy, and where does that energy go? Right. Now this is a little bit different than the bucket and the pulley. Right. Now we got the short toilet paper roll. Right. But go ahead. Set up. What do you think could be an equation that could eventually navigate somewhere? That could describe that. Okay. So you have this toilet paper roll. You're holding on to the paper. It's unraveling as it's falling. So where does the energy come from? Where does the energy go? Maybe there's some height change. But if I'm doing an energy equation, height change is going to be somewhere in there too. Okay. All right. So see what you guys came up with. What do you guys think is probably the source of the energy right here?
MG.
Yeah, MGH. Probably the same as last scenario, right? The fact that this toilet paper roll is falling. Yeah, it is MGH, right? Right. And as it's falling, it's unraveling. It's really thin paper, so the radius probably doesn't change a whole lot. Wouldn't worry about that so much. Okay. But the energy goes where plus also where? Yeah, linear kinetic and rotational kinetic. And how do you write that in physics? What and plus what? 1/2 mv squared and then plus 1/2 I omega squared. Can that be it? Yeah, this 1/2 mv squared is like if you point a radar gun at the center, that it's going to read this v. Okay, and maybe this whole roll has some mass m. Okay, and then if it as it's rotating, that how fast it's spinning is represented by omega, and then 1/2 mr squared probably gives you pretty good value for I. Okay, right, something like that. No, okay, same as before. Is the linear speed of it falling related to how fast it's rotating omega? Are these related? Yeah, I think that goes back to this one too. Isn't that like this here? So again, I could substitute out either way. I could, okay. Let's say I want to solve for v. So I know omega is v over r, and I could substitute out the omega. Okay. Right, so that's the next step right there. Okay. How about this? I did another substitution. I substitute for I call it 1/2 mr squared. Okay. How about this? Guys, look at this line right here. Suppose we're at this line. All right, again, critical thinking. Just want you guys to see the big picture here. Which variable or variables, what's one variable you think cancels out? What's going to cancel out? Here's a hint. I see
Mass.
1, 2, 3 terms. Yeah, mass. Yeah. I see 1, 2, 3 terms. Okay. So if they all have something in common, they can cancel out. Yeah, the mass. Okay. What that means is, suppose I had how about a roll of aluminum? Real big, bulky, way heavier. Okay. Could it basically be modeled by the same equation? Yeah, pretty much. Okay. Okay. Also, there actually is one more thing that cancels out. Does anybody see it? Radius. Because it's got radius squared here, numerator, denominator. Yeah, that cancels out too, right? Which means if you have a small roll versus a big roll, again, ignoring the hole in the middle, right? That doesn't make a difference either, right? Just the fact that it's a solid cylinder, right? That matters. Right. So anyway, you can keep finishing this out. And here's the answer for the linear speed. Guys, let's go to the comparison here. Remember, I said you just drop something and free falls. Who remembers from last semester? What's the crash speed of something that just free falling? It was always square root of what? 2gh. You guys remember square root 2gh?
Right.
Yeah. Right, the Galileo question. Right. And this, guys, is this faster or slower than that? Slower, because 4/3 is like 1.33, which is less than 2. Yes, this would be slower, right? Which makes sense because some of the energy is converting into making the thing rotate. Okay. Now, you could start from this. I mean, this would be the most obvious question you could get that conservation of energy would let you solve, right? But you could ask some other questions too, like what's the linear acceleration, for example, right? And so I brought in kinematic right here, right? And then you do a little kinematic substitution, you get like that. Okay. And now there is a completely different way to solve this, right, which is going through torque. Right? Again, I just want you guys to see the big picture and think, okay, kind of see how that works. Right? Do you guys see now torque? I have to think about the individual forces. Do you guys see that there's the weight pulling down, and I put that acting through the center, right? And then there's this tension pulling up, and that's acting at the edge. And there's this offset distance, which is the radius, right? Which is what you need to have a torque. You need more than one force. You need them at different locations on the object to induce rotation, right? Uh, and okay, no, I'm not going to ask you guys this level of detail in the quiz. Maybe just see it today, right? But if you go to college, this might be applicable, right? Which is when you use this particular method, you do have to consider that it's not rotating about its center. It's actually rotating about this point on the edge. Do you guys see that? Right. Which means the rotational inertia is different than what we use for conservation of energy because it's not rotating about the center anymore. Right. So you do have to bring in. Okay, we're getting a kind of a little more technical here, but parallel axis theorem. The fact that if something's rotating about a point, like a ball rolling across the floor, is actually rotating about its bottom point, right? The offset distance, in this case with the radius, you do have to consider that. Right? So parallel axis theorem. And the overall inertia is actually more than the value from the table where it's rotating about the center. Okay. Right, that's what this is right here. Okay. Right, big picture too. Do you guys see that with this particular method? You can actually solve for the acceleration first, and then you go kinematic and solve for the crash speed. Right? Versus the energy method, you would be solving for the speed first, and then you could solve for acceleration from kinematic. Right? So there's different paths to the forest, but they all lead to the same answer. Right? All right. Now I do want to have you guys solve a ball rolling downhill. Okay. Here's a basketball. Okay. Let's see first. Can you guys set up the energy equation? Okay. So I got a ball rolling down an incline. We'll do a basketball together, and then we'll switch to a different kind of ball, and I'll throw some numbers at you guys. Okay, you guys ready for that? Okay, so in a few minutes, I'm going to throw some numbers and see if you guys can solve the numbers. And it won't be a basketball though. Okay. But it might have a similar setup. So what energy term do you think starts right here?
MGH.
Yeah, MGH. Right? That's like the source of energy. Right? And by the time the ball gets to the end, it has what type of energy? Yeah, kinetic 1/2 mv squared. But is it also rolling? So it also has what? Yeah, rotational kinetic. Yeah. Right. So wouldn't this be the setup right here? Okay. Right. Yes, that. Okay. Now, guys, pay real close attention here because this one I will walk you guys through step by step, and then I'm gonna switch the type of ball and see if you guys can solve it. Okay. Right. So we got this. Now, this there's really one object we're focused on, which is the ball, which means that this I and this M both refer to the same object. And since I has something to do with the mass of the object, I think these are related to each other. Isn't that true? Okay. Now we're going to use an energy method, which means I don't have to consider the parallel axis theorem. I lost the paper I'm looking for. Oh, here it is. Okay. So, guys, for this I, I'm going to substitute this value for the basketball because the basketball is basically a spherical shell. Is that okay? 2/3 m squared. Okay. But there's another substitution I have to make because there are more variables that are related to each other. Is which other variables in this equation are related to each other?
Yeah.
Exactly, the v and the omega. Okay. The faster the center of the mass of the ball is moving, the faster it's rolling to get there. Okay. And what's the connection again? I can substitute out omega with what?
V R.
Yeah, v divided by r. Yeah, v over r. Okay. That's here it is. Okay. This omega is this v divided by r. You divide the r down. So I can solve for v. Okay. So if you're asked for linear speed, okay, that looks like that. Right. The 2/3 I left orange because that's particular to, say, a basketball shape. Okay. Okay. By the way, here, this real side thought. Hey guys, is h equal to L times sine theta? Right? Is that true? Right. I did put that here. It may be helpful depending on what you're getting. Okay. Anyway, if you do some algebra, this ends up being the speed at the bottom of the linear speed for the basketball. That's this linear speed. So if you point a radar gun right at the center, it's going to read whatever that is. So whatever his height is, gravity field, right, you run a square root 6 fifths GH for basketball. Okay. There's another method. You can go through torque. You have to consider parallel axis theorem. It's a little trickier, but it does lead to the same answer. Okay. All right. And what I want to do with you guys now is let's do a solid ball. You see a solid ball rolling downhill? Okay. Solid ball rolls downhill. And I'm going to give you guys some numbers and see if you can come up with the correct numerical answer. So let's do this in your notes. Okay. So what is the linear speed of the solid ball rolling down the incline? Okay. Okay. I should also say without slipping. I forgot to mention this, but if there was no friction with the surface, right, you guys ready for a weird question? Is what if there was no friction? What if I have an air hockey table and it's kind of levitating and I let it go? Is it even going to roll at all?
No.
Yeah, it turns out it won't. Yeah, right. So you do need a static friction force to induce, or you need friction to induce rolling. Oftentimes these are framed as like, oh, rolling without slipping. Right. So there is friction, but it's not taking energy out of the system. Right. And so let's do this setup here. So I'll give you guys this incline. All right. All right, let's get the solid ball right here. Okay, and it's going to be rolling, rolling, rolling until eventually it reaches the end. Okay, it's going to have some linear speed. I'll call it V. Okay. Let's say that this length right here, the length of the incline is about 2.5 meters. And let's say this is pitched at an angle of about 30 degrees from the horizontal. And I'll give you the mass of the ball in case that matters. Maybe it does, maybe it doesn't. Okay. Let's call it 5 kilograms. Big old bowling ball. And here I'll give you the radius of the ball as how about 0.25 meters. Okay. Let's call gravity field 10 meters per second squared. I think that's plenty of information. Yeah, that'll do it. Okay. So go ahead. I'll give you guys a head start on that. About a minute head start. Okay. So I'll kind of walk you guys through what a basketball rolling down the site. Okay. So I'll switch out the type of ball. Throw a bunch of numbers at you guys. And what's the linear speed at the bottom? Let's go ahead. Solve for linear speed. Linear speed. Okay. We gotta recommend using that energy method. Okay, so use the energy method. Ooh, tell you what, I'm gonna solve this off camera. First person to tell me what I get, I'll give you that Hershey's bar.
Oh, it's on.
Yeah, all right, so I'm gonna pause this video and solve this because this might take a good couple minutes. All right, recording resume just for intermission here. Right, so I tried this a couple ways. I keep getting the same answer. I haven't heard it yet, but here, just put this on recording. I did give you guys a hint. So this poster's taken in class, and you guys told me that this would be useful right here. So this is part of it. So you do need this. Okay, you do need this. Okay, in fact, this is solid ball. All right, go back, pause this again. See if anybody gets this. All right, back recording. All right, got a winner. Anna, it's a chocolate. Oh yeah. Oh yeah. All right, so show you guys this is what I was thinking. All right, so here's your conservation of energy. Right. If you just like this you see a few of these steps today. Right, so the source of energy is this MGH. And by the time the ball rolls to the bottom, it has this linear kinetic, 1/2 m squared, this 1/2 I omega squared. Right. And now this is where you need where'd it go? Right. All right. Okay, here we go. This is where you need this rotational inertia of a solid ball is 2/5 mr squared is how it works out. Okay. That's going to substitute in for this I, 2/5 mr squared. And then for the omega, you do V over R. Now it's also being squared, don't forget that. Okay. Now I was really tempted to start slashing variables that cancel because they do cancel out that way. I mean, I should just go ahead and plug it in, right? Even though they will cancel anyway. It doesn't matter guys, the fact that I gave you the mass of the ball and radius of the ball, those are completely irrelevant at the end of the story anyway. Okay. But if you just process, right, you plug in everything I gave you. You don't know this v, which is being squared both in this term here and this term here, so you can factor this out. Or actually, you know what? You can actually add these two together. That's what I did here. Okay. So then divide this down and take the square root, and the linear speed's 4.23 meters per second. Okay. So you plug in the numbers here and then crunch the algebra after that. Okay. Okay. Any questions about that process? Okay. Alternatively, you could solve this in terms of variables, which is done right here. Okay, so the answer is always this expression. Let's try this out. Try this expression. So I'm claiming that every solid ball is going to have speed of square root of 10 over 7 times gravity. Now for gravity, we use 10 meters per second squared. I told you to use that. Okay. And then the height. Oh, but you know what? I didn't actually give you the height. What I did give you was the L and theta. But I forgot to mention that. You guys, what is this height in terms of L and theta? What is it? L sine theta. Yeah, L sine theta. Okay. In fact, guys, who remembers what is sine of 30 degrees? 1 over 2. Yeah, 1 over 2, 1/2. Okay. So this is 2.5 meters times 1/2, or 1.25 meters, isn't it? Isn't that the height change? 1.25 meters? Okay. And that goes in right here. Bam. So times 1.25 here. Okay. And I should get the same number. There it is. There it is. It's the same thing. Aha. Same thing. You see that?
Wait, so to solve the kinetic energy of any solid ball, it's just square root 10 over 7 d8.
Okay, yeah. So guys, this solution is particular to this scenario. If you have a solid ball that's rolling on an inclined plane, yeah, then this linear speed will always be this. Okay, so this could be true for a marble or a bowling ball.
Can you put the poster up of how to get the like H, L, and then the base? Because I forgot too.
Oh, trigonometry.
Yeah, I didn't learn too much about like the sign.
Let's see if I can find trigonometry. Okay. Yeah. All right. Okay, so let's go way, way back. Okay, so you guys remember this right here?
Yeah, it's just hard for me to remember.
Yeah. Okay, so here's like the math definition. Sine is opposite of our hypotenuse. Cosine is adjacent of our hypotenuse. It's all relative to this theta. Okay. Tangent's opposite of adjacent. Okay. But common physics applications, like what we just did is actually this box right here, is if you know the hypotenuse, you can multiply by sine to get the opposite. Okay. Multiply by cosine to get the adjacent. Okay. And then, well, tangent has something to do with the two sides. So if you know the two sides, take the inverse tangent. That'll be the theta. All right, so come on. All right, let's got those.
But are you gonna put that poster up again or no?
Hadn't thought about it. Here, put myself a note. All right, so well, I'll hold that out now. Yeah, see about that. That is a useful poster. Yeah, it's useful all year. All right. Here, I got actually posters for all different rolling objects. So there's the basketball, there's the solid ball. Right. Here's what a ring looks like. Okay. You see over and over and over, these are following formats. Square root of something times GH. For a ring, it's just square root GH. Okay. All right. Now I got one more, and it's kind of the last poster in this whole section. Okay. Let's have a roll race. Roll race. You got all these objects at the top of this plane, okay. And somebody's going to win, and there's going to be rank order to how they're going to finish. Okay. Now, I do have one frictionless lane. You have to have one lane with no friction, and an air hockey puck right here. Okay. Guys, show of hands. How many of you think that the air hockey puck that doesn't have to spin at all is going to beat all these four rolling objects? Yeah, air hockey puck always wins. Right? In fact, what do you think the speed of the air hockey puck is at the bottom of the plane? Square root 2gh. Square root 2gh. Right? Galileo question. That's regardless of the angle, as long as it's frictionless. Right? But what about these rolling objects? Now, you've seen from these last few that the mass and the radius end up canceling out, so that's irrelevant. You guys see that? Mass and radius cancel out? Okay. But what does matter is how the mass is distributed. Like, is it a ring? Is it a basketball? Is it a bowling ball? Right? How's the mass distributed? Okay. So that's what's relevant. Right. So now these are in order of something. Do you guys see that the bowling ball, its mass is closest to its axis of rotation in the center? And then as you go to the right, the mass gets progressively spread further out. Like the cylinder is a little more spread out than the bowling ball is. the basketball is a good amount spread out because now its mass is all on the surface, right? And the ring is even more spread out relative to its axis of rotation. Okay, right. So they're going to finish in some order. Right? I guess among the rolling objects, either the bowling ball or the ring is going to win, and the other one is going to come in dead last. You guys see that?
Yeah.
Right. But which one's which? Can you guys reason? Right. And one way to reason this is, I think, whichever one has the most energy diverted into its rotation, proportional to its mass and radius, whatever, right, would have to lose. Which one has more of its energy proportionally going into linear speed would have to finish the race first and win. Does that kind of make sense?
Mm-hmm.
Right. So which one's which? Right. I'm going to say show of hands. Which one do you guys think wins the race? It's either going to be the bowling ball or the ring. Okay. Who's going to win the race? Say it gets down fastest. Let's say proportionally more of its energy goes into linear rather than rotation. Okay. Right. All right. You guys ready for this? Right. Show of hands. How many guys think the ring wins the race? Who says the ring wins? And who says the ring? Who thinks the bowling ball wins the race? Yeah. All right, and there's your rank order. Right. I don't know if the positions are exactly correct, but that is the correct rank order. Right. Be like that. Right. Okay. All right. All right. Let's look at. Okay. We've got a few minutes. All right. Let's see. Everybody be able to knock out one of these. All right, so puzzles. What's a puzzle we can do in about 4 minutes here? How about the steering wheel? Let's do a steering wheel right here. Number 74. I think we can knock this out in a few minutes. Number 74. 74. Yeah, steering wheel is rotated 128 degrees. Degrees. Its radius is 22 centimeters. How far would a point move on the edge? How far on the edge? You guys start solving that. How far would a point move on the edge?
Oh.
Here. Okay. Are you guys thinking about this one right here? You guys think of that?
Yeah.
Okay. So how far would a point move? Which formula? Is it the top, middle, or bottom? Yeah, okay, yeah, top one. Something about displacement or distance, something like that. Okay. So can you guys use this? Okay. All right. So we got what's that? 74. Got this rotating. It says it rotates 128 degrees. That's approximately like that.
Like something to freak out.
128 degrees. Yeah. Okay. And this radius right here was 22 centimeters. Right. And we want to solve for x. What's this distance? What's the point on the edge of the steering wheel from there to there? Which is solve for. Yep. So x could be theta times r. Okay. And I know r is 22 centimeters. Okay. Guys, can I plug in 128 for theta in the calculator? No. No. Well, why not? Or what should I plug in?
Radians.
How many radians? So let's say theta equals, now it is 128 degrees. Guys, how many degrees is equal to how many radians?
2 pi.
2 pi radians is 360 degrees? Yeah?
Yeah.
Is that true? Okay. You could do that. You say 360 degrees is 2 pi radians. Okay. A lot of times I'll do pi over 180. Okay. Either way, same thing. 128 times 2 pi on 360. That's right. And that looks like 2.234 radians. Okay. And that is the number that feeds into the angle. Okay. So now x equals 2.234 radians. Okay. And we do have 22 centimeters, so the answer will be in centimeters. Okay. So times 22. Okay. I'm looking at 49 centimeters. There you go. And that's our pause point today.